Hi everyone, I'm Daniel, and I'll be presenting this work that I've been working on with my colleagues at the University of Toronto. So the focus of the work that we've been doing is on dealing with the effects of bugs in file systems. There was a study that was presented at FAST last year which concluded that 40% of file system bugs can cause data corruption. And one of the big problems with file system bugs is that the corruption they cause is persistent. You can't just reboot your way through it. And this corruption is also silent, so the user doesn't necessarily know that anything has gone wrong until they try to get their data back. Corrupted metadata is especially problematic because a few corrupted bytes of metadata could result in many more bytes of data being lost or inaccessible. So existing reliability mechanisms can't catch bugs in the file system software because they're usually aimed at problems lower down in the stack, like hardware failures or blocks getting eaten by drivers. So hardware redundancy and checksums can't really help us here, because if the file system produces a block which it has corrupted, and then checksums that block, and then replicates that block, the corrupted block has now just been well preserved, but it's still wrong. So our aim is to ensure that the file system is not able to cause corruption of the data that's on the disk. To do this, we built the Recon system, which was first presented at FAST 2012. And Recon checks the consistency of every transaction at write time. So it takes consistency checks from the FSCK offline tool and applies them in an online fashion to the transactions, which prevents corrupt transactions from reaching the disk. So to illustrate Recon in action, here we see the file system writing a number of updated metadata blocks to the journal. Now, Recon is situated in the block layer, and so it can observe all these writes as they happen. So when the file system writes the commit block, this signifies that the transaction is complete, and Recon can check the contents of the blocks that have been written to the journal to ensure that they're mutually consistent. Then if they pass the checks, we can forward the commit block to the disk and allow the transaction to be committed. So because Recon depends on seeing a commit, it's depending on the file system using some kind of transactional mechanism like a journal. Recon depends on this transaction mechanism working correctly. For instance, the contents of the journal need to be eventually flushed to their final destinations. And these writes aren't checked by Recon because they're not part of the currently committing transaction. Unfortunately, of course, like all software, these transaction mechanisms also have bugs in them. For instance, in a journaling file system, updates are supposed to be written to the journal first. If the file system bypasses the journal and just writes a block to its final location directly, this could corrupt the file system on a crash. And as another example, say we flushed a block from the journal incorrectly to the wrong location. In this case, we've potentially lost the updates that the block contained, as well as trashed the block that we overwrote. So our problem is that checking the internal consistency of each transaction is not sufficient. Bugs can still corrupt the on-disk metadata by violating the semantics of the transactional crash consistency mechanism. So our solution is to extend Recon to check the behavior of the transaction mechanism at every write instead of just the consistency invariants at the commit point. So to outline how we do this, first I'm going to characterize the behavior of the bugs and the invariants that we use to catch them. Then we can actually walk through the specific invariants for journaling and shadow paging. And finally, I'll discuss our implementation and an evaluation of its correctness and overhead. So modern file systems maintain three properties: consistency, atomicity, and durability. Atomicity and or consistency is what Recon was checking, which is the consistency of the metadata being committed. Atomicity and durability are the responsibility of the transaction mechanism. So by atomicity, we mean that a group of updates to multiple blocks will become durable or all at once or atomically. And by durability, we mean that once an update has been committed, then it will remain there until it's superseded by an update in a future transaction. You might have noticed that isolation is missing from this list of what's traditionally ACID properties. And this is because for performance reasons, file systems don't usually provide isolation. Instead, they group many operations from multiple threads together into one big transaction called a group commit. So Recon checks consistency, but by only checking consistency, Recon can miss bugs that violate atomicity or durability. So bugs like this show up in a few different ways. They can appear as missed writes or forgotten writes. They can show up as overwrites, or writes could be reordered across a commit boundary. Or the contents of a block could be corrupted in mid-flight. And all of these eventually result in an unsafe write, which is about to violate atomicity and durability, unless we can prevent that block from reaching the file system on disk. So to catch these unsafe writes, we need atomicity and durability invariants. So atomicity and durability invariants verify that committed transactions are safe. They do this by checking every write to make sure that the location of each write is correct. And so this is why we call them collectively location invariants, because they're concerned with where we're writing to. We have to verify every write before we allow it to reach disk, because any write could potentially violate atomicity or durability. On the other hand, the consistency invariants apply to the contents and semantics of the transaction. And checking consistency involves constraints between multiple blocks. And so we have to wait until commit time before we can make these checks. So Recon already checks the consistency invariants, and what we're adding are the location invariants for atomicity and durability. So by checking consistency and location invariants together, we can provide the strong guarantee that the disk will remain consistent in the face of arbitrary file system bugs. While the file system can use checksums and replication to protect itself against errors in the I/O stack, the invariants sort of sit below the file system and protect the file system from itself. So now I'd like to walk you through the actual details of the location invariants. In particular, we've implemented location invariants for two types of transaction mechanisms, journaling and shadow paging. So unlike the consistency invariants, which are file system specific, the location invariants are actually just derived from the semantics of the transaction mechanisms on their own. So I'm going to describe the invariants for journaling, but first let's just take a quick walkthrough of how journals work. Journaling is a four-step process. First, we write updates to a log. Then we can write a commit block to that log to mark all those updates as committed. Then we flush committed updates to their final locations. And finally, once those blocks are all in place, we can free the blocks in the log that the transaction was using. And so each of these steps corresponds to a location invariant. The first is the log invariant, which is that all writes in a transaction have to go to a free block in the journal. So we write 3 blocks to free blocks, and this is okay. If instead we wrote blocks that were not free in the journal, we'd be violating the durability of what we'd already committed. The second invariant is the commit invariant, which is that commit occurs only after all the blocks in the transaction have reached the journal. So first we write some blocks, then we write the commit block. If, for instance, let's say we didn't check this and only some of the blocks in the transaction reached the journal. If commit reaches the journal, then we have this block of unknown content, and on a file system crash, when we replay the log, that red corrupt block is going to end up overwriting some metadata in the file system. The third invariant is the flush invariant, and this is that overwrites in the file system must match a block in a committed transaction in the journal. So this is ensuring that we have logged everything that we are now updating in place. In this example, the light blue blocks are part of a committed transaction, and the yellow blocks aren't. So we can flush all the light blue blocks to the disk, but it would be a violation of the invariant to flush block number 10 because it's not part of a committed transaction yet. And finally, we have the checkpoint invariant, which is that the journal blocks can only become free once all the blocks in that transaction have been flushed. So now that our light blue blocks have reached their destination on the disk, we can mark those blocks in the journal as being freed and reuse them for a transaction in the future. So these are the four invariants that protect the atomicity and durability that the journal is supposed to get us. Now I'd like to talk about shadow paging. In shadow paging systems, we have a tree of metadata blocks. And first, updated versions of blocks are written to free blocks on the disk. So then, once those blocks are all in place, the commit occurs when a pointer to the root of the tree is updated. So this means that updates in the new blocks all become visible atomically. And this leads to two invariants for shadow paging. The first we call no overwrite, which is that blocks shouldn't be overwritten until after they're deallocated. And this is the essence of a copy on write system. The second invariant is the commit invariant, which is that the superblock or the commit block should only be written after all the new blocks have been flushed to the disk. And this is very similar to the commit invariant for the journaling invariants. So now that we've talked about the invariants, let's talk about how we can implement them. Checking the invariants at the block layer requires certain file system information to be available to us. In particular, allocation information is necessary to detect whether or not a block can be overwritten. It's also important that we can distinguish between metadata and data blocks efficiently, because some invariants apply only to metadata blocks. This happens in particular when you're doing metadata-only journaling, where you have to check all the journal invariants for metadata blocks, but data blocks can be freely overwritten. As we saw earlier, consistency checking requires commit points, clear consistency points, but the location invariants also require these commits. And this is because it needs to make its decisions based on a committed version of the allocation information and not some potential future version of what the allocation state looks like. And finally, if we want to make sure that the committed metadata is consistent, Recon's original consistency checking mechanisms require us to be able to identify the contents of metadata blocks as well. So a key takeaway is that the consistency and location invariants depend on each other. The consistency invariants depend on the location invariants to preserve the file system's atomicity and durability. And the location invariants depend on the committed state, which has been verified by the consistency invariants. So we implemented location invariants for ext3 to test the journaling invariants, and for Btrfs to test our shadow paging invariants. And we did this by using Recon's existing infrastructure at the block layer for intercepting I/O and for interpreting the metadata of these file systems. We also added a metadata bitmap to ext3 in order to satisfy the requirement to efficiently distinguish between data and metadata, because ext3 sometimes will co-locate data and metadata blocks in its block groups. Checking the journal invariants also required some additional bookkeeping in memory. So as blocks are written to the journal, we create in-memory records of these blocks which track the final destination of the block and the transaction that it's part of. We also keep a checksum of the block in memory in order to track whether or not we've seen that version of the block being flushed to its final location. So as transactions commit, we append new versions of the blocks to our lists for each transaction separately. When a write to a metadata block happens, then we can traverse the list of journaled blocks, journaled versions of that block, from the newest to the oldest until we find a match. Once we find a match, we can mark that record as flushed. And once all the blocks in the transaction have been marked as flushed, then according to the checkpoint invariant, it will be safe to free that transaction. So to evaluate the correctness of our approach, we simulated atomicity and durability bugs by injecting faults into the transaction mechanism. And so the faults we injected were lost writes, random corruption of portions of blocks, and misdirecting writes. And we did this in a type-specific manner, so we tried all of these corruption types based on the target type of block. So this included the metadata structures in the journal itself, the journaled metadata blocks, the metadata blocks elsewhere in the file system, and also we misdirected data writes to overwrite metadata or the journal. And this resulted in 16 different pairs of fault type and target block type, and we ran 10 corruptions for each pair. So this resulted in 160 total corruptions, of which we caught 138. So why did we miss 22 corruptions with our lovely, shiny atomicity and durability invariants? What happened is that, especially with the journal metadata structures, there are large portions of the blocks that are unused. And so random corruptions to these areas of the blocks don't really affect the integrity of the file system at all, and our invariants don't trip because of this. The other 7 blocks were lost writes that were metadata flushes to the final destinations, but these also didn't threaten file system integrity because there was a future version in the journal that could have been replayed, even if that write was lost. And so none of these missed corruptions affected file system consistency, and we checked this by running fscheck after every corruption. So to evaluate the overhead of our system, we ran some benchmarks using FileBench on a very simple server, and we tried 3 different workloads. The varmail profile performs a lot of synchronous small writes. The web server workload is a read-heavy workload with a few small updates, and the MSNFS profile is the FileBench's network file server profile that has been customized to use a realistic distribution of file sizes from a Microsoft survey of desktop file systems. So for our performance experiments, we compare the native file system versus the original Recon with only the consistency invariants to updated Recon with the location invariants added. On the y-axis, we have the operations per second throughput as measured by FileBench. And as you can see, the consistency invariants add negligible overhead. In fact, it's often just within the error bars. In addition to that, adding the location invariants on top of this doesn't really incur any additional penalty. For the Btrfs file system, we also see that in some cases the consistency invariants don't really cost us much, except in the case of the web server benchmark. And this might be surprising because web server is a read heavy benchmark, and all the work that Recon is doing is on the right path. But this is actually because there are a large number of timestamp updates that is generating a lot of metadata churn for Recon to check the consistency of. So we take a fairly large hit on the consistency checking, but adding the location invariants on top of that doesn't really increase our overhead. So in conclusion, protecting on-disk metadata requires checking the consistency, atomicity, and the durability invariants. The consistency invariants check the contents of the block that we're writing in a new transaction, and the atomicity and durability invariants check the destination that we're writing to. Certain file system features enable checking invariants from the block layer efficiently. These are the availability of allocation information, easy distinction between metadata and data, easily identifiable commit points, and the ability to determine a block's identity through either back pointers or some other mechanism. And in the paper, we actually survey a number of file systems and discuss them as far as they relate to these features and how easy it would be to implement invariants for those file systems. Finally, we conclude that the location invariants add very little additional overhead on top of the consistency invariants, and we implemented the invariants and evaluated them for ext3 and Btrfs. I'll take questions now.
Hello. Okay. So great work. I loved the previous paper. This is really fun too. I guess the question is, it's great that you can detect these things. Have you given any thought to what you might do after you detect some sort of problem? Because it seems I'm wondering both. Are there a set of cases you can easily identify where you could essentially remedy the problem in line? Just delay that commit record until, in the hopes that the rest of it comes along. And secondarily, is there stuff you can do to look at it and say, oh, I've got some really strong hints about the bug report that needs to be filed here?
So in terms of figuring out what bug report to file, we haven't really thought about that at all. But I think you're right in that in some cases it's actually optimistically delaying the commit is something that you could do, or just suppressing a write in hopes that it'll show up in the transaction later. But I mean what we do right now is EIO, because our first priority is making sure that nothing gets overwritten, and so the writes that we're trapping are the write. Is the write that is going to trash something. So if preventing that write and then just hoping that things will improve in the future, could keep the file system in a consistent state. But if something's already going wrong, you probably want to know about it as soon as possible.
Yeah. So on slide 29, when you talked about a corruption that wasn't detected in terms of losing metadata flushes that weren't necessary, wouldn't that actually be a good thing that the file system realized that since metadata block is being modified in another transaction to not actually flush it to disk and actually wait until that second transaction is done?
Right.
So it would seem to me that that's actually more of a flaw in your testing as opposed to something that the file system was doing wrong.
Well, so I mean, in this case, the file system was, flushing these blocks out when it didn't necessarily need to because there was future versions in the journal. We were losing those writes, as part of our just, fault testing. But it didn't matter whether or not those writes happened is basically what the result was.
Right. So in fact, if the file system could have avoided doing
that, yeah.
It's actually the right thing, because in fact, the real disaster is if you lose a metadata flush and then a checkpoint happens.
Yeah, exactly.
Right.
Harume Kuno, HP Labs. On slide 33, why was performance better when you checked both consistency and location versus just consistency?
It is a mystery.
Thank you.
The error bars are wider once we start running Recon, and so if you look at the high side of the error bars for native Btrfs and the low side, they're close. But I have a couple additional theories why it's looking like we're getting better performance, and you can ask me afterwards because we're not really confident in why. I think if we ran these experiments more extensively, you'd see that performance is pretty much just comes out in the wash. Yeah.
Yes, I was wondering if this work could potentially handle a journaling system that didn't have an explicit write to disk for either the commit or the checkpoint, that those were purely synthetic operations that were logical and were never physical.
So it depends. So if your logical journaling is just sort of journaling at the level of the system call, for instance, in order to even check the consistency of those operations, we would have to wait until they are materialized in terms of writes to the disk. The invariants wouldn't really be applying to what you're writing to the journal, but they'd be applying to the blocks later. And I don't think we've really thought out exactly how that in that case, what's the distinction between the consistency invariants and the atomicity and durability invariants? We're just sort of waiting for them all to get there. The important thing is that we can sort of cross off every operation in the journal according to the operations that we've seen before we remove them from the journal.